Today we're going to decode what is basically a secret language. It's the language mathematicians use to describe symmetry, this hidden structure you can find in, well, pretty much everything, from a Rubik's Cube all the way to the laws of physics. We are diving deep into group theory. So, let's start with a puzzle. Think about a scrambled Rubik's Cube. Then picture the perfect, repeating lattice of a crystal. And then imagine the infinite stretch of integers on a number line. I mean, on the surface, these things couldn't be more different, right? But believe it or not, they all share a really deep fundamental property. Any ideas what it might be? The answer, in one word, is symmetry. But we're not just talking about the kind of symmetry you can see with your eyes. This is about a much deeper structural symmetry. It's a pattern of transformations that you can perform on an object that leaves it looking basically unchanged. And mathematicians, of course, have an incredibly powerful way to describe and quantify this. This universal pattern is captured by a really beautiful mathematical object. It's called a group. And honestly, it's the foundational concept for understanding symmetry in just about everything, from particle physics all the way to solving puzzles. So, what exactly is a group? Okay, think of it like this. You've got a collection of things, those are your elements, and you have one single rule for how to combine any two of them. Now, these elements could be anything: numbers, rotations, even the different moves you can make on a Rubik's Cube. And the operation could be something like addition or maybe combining movements. But, and this is the important part, for this little system to be a true group, it has to play by 4 very specific rules. Let's get into what those rules are. And these aren't just some arbitrary list, you know? They are the absolute essential laws that any system of symmetries has to obey. You can think of them as like a detective's checklist for identifying a group out in the wild. So, as you can see, there are 4 P rules or axioms. First up is closure. This just means that when you combine any 2 actions, you stay inside the system. You can't accidentally create something totally new. Second, we have associativity. All this means is that the way you group the operations doesn't mess up the final result. Third, there absolutely must be an identity element, sort of a do-nothing move that gives us a baseline. And finally, every single action needs an inverse, a way to undo it and get right back to where you started. Okay, now that we have our 4 rules in hand, let's go hunting. We're going to check out a couple of mathematical suspects and see if they've got what it takes to actually be a group. All right, our first suspect is one we all know and love, the set of all integers, positive, negative, and 0. The operation we're going to test is just simple addition. So the big question is, do the integers under addition form a group? Let's run down the checklist. Closure? Yup. Add any 2 integers, you always get another integer. Check. Associativity? Absolutely. Addition is associative. Check. Is there an identity element? For sure. It's the number 0. Adding 0 doesn't change a thing. Check. And what about an inverse? Well, for any integer, let's say 5, its inverse is just -5. Add them up and you get back to our identity, 0. Check. It's a perfect match. The integers form an infinite group. Okay, cool. But what about something geometric? Let's take a look at a simple square. What are its rotational symmetries? Well, we can rotate it 0 degrees, that's our identity, or 90 degrees, 180, and 270. Any further, and we're just repeating ourselves. So those 4 rotations are our elements, and the operation is just combining them, one after another. And this table right here just shows the closure property perfectly. Look at it. If you do a 90-degree turn, and then you follow it up with another 90-degree turn, well, that's the same as doing a single 180-degree turn. And 180 is still in our set. You can pick any 2 rotations, combine them, and the result is always one of the other 4. It's a closed system. This finite set of 4 rotations absolutely forms a group. Okay, so now we can identify groups. This is where we get to the first really major breakthrough in this whole field, a super powerful numerical rule that governs the structure of all finite groups, discovered by the brilliant Joseph Louis Lagrange. Lagrange's theorem it's just stunning in its simplicity and its power. It says that if you have a finite group and you find a smaller group that's living inside of it, we call that a subgroup, then the size of that little subgroup has to evenly divide the size of the bigger group. No exceptions. So this is the crucial point right here. The size of a subgroup isn't just random, it is strictly constrained. If you have a group that has, say, 12 elements in it, its subgroups can only have sizes that divide 12. So 1, 2, 3, 4, 6, or 12. There is no way it could have a subgroup of size 5 or 7. It's impossible. This theorem is like a powerful filter, giving us a huge shortcut in understanding a group's possible internal structures. Now, that seems like an incredibly neat and tidy rule, doesn't it? Maybe a little too tidy. So, does this powerful theorem really tell us the whole story? Or is there a twist? Well, this leads to a pretty natural question. We know that if a subgroup exists, its size has to be a divisor. But does that work the other way around? If we pick a number that divides the group's size, are we guaranteed to find a subgroup of that size? And this is where we have to be really, really careful. Lagrange's theorem is a one-way street. It gives us what's called a necessary condition. The size must be a divisor. But it's not a sufficient condition. It doesn't promise that a subgroup actually exists for every single one of those divisors. And here it is, the famous counterexample. There's a particular group of symmetries, it's called A4, and it has 12 elements. Now, the number 6 obviously divides 12. So, according to Lagrange's theorem, a subgroup of size 6 could exist. But it turns out it doesn't. There is absolutely no subgroup of size 6 in A4. The group's internal structure just forbids it. And this proves something really profound. Group theory is about way more than just counting. So this twist, it forces us to look deeper. If size isn't everything, then what is? Well, the answer lies in the quality of a group's internal structure and the relationships between all its different parts. To really see the true structure, we have to find special kinds of subgroups, and the most important ones are called normal subgroups. You can think of them not just as any old subgroup, but as these perfectly symmetrical building blocks. Their special properties are what reveal the deep, hidden architecture of the entire system. And to compare different groups, we use a special kind of map called a homomorphism. It's sort of like a translator, but one that doesn't just convert words. It preserves the grammar and the sentence structure of the original language. It lets us see how the pattern of one group can be perfectly mirrored inside another one. So here's the real takeaway. To truly understand symmetry, you can't just count the elements. It's not enough. You have to analyze the quality of the connections between them, the nature of those special subgroups, and these structure-preserving maps that link them all together. And that leaves us with a final thought, doesn't it? Group theory gave us a language for symmetry, this invisible structure that we see the effects of everywhere. It really makes you wonder, what other invisible structures are out there governing the very fabric of our reality, just waiting for us to find the right language to finally describe them?